All right, and we are back for our Pset 5 solution video. So let's go ahead and look at the stress strain curves below. Which material is, and actually we'll go ahead, stiffest, toughest, strongest in terms of UTS, highest yield strength, most ductile, brittle. So stiffest, we're looking for the highest Young's modulus. So they're all pretty similar, but I would say probably the green. Toughest, assuming they have the same volume, I think it's a safe bet to say blue. Strongest in terms of UTS, which is highest ultimate tensile strength, that's also going to be blue. Highest yield strength, I would say it's probably going to be the green, somewhere around here. So let's go ahead and say green. Most ductile is going to be the highest strain at failure, which is also looks to be blue. And then finally, most brittle, lowest strain at failure, that's going to be our green. So we can list that out. Fantastic. For the orange curve, indicate the quantitative value of the strain at failure, failure stress, yield stress, ultimate tensile stress. So this is our strain at failure. It's about 0.6, probably 7, something like that. Failure strain, failure stress would be basically right here. So about 60 megapascals. Ultimate tensile strength is also the same as the stress at fracture when it fails. Yield stress, I would say probably around right, I'd say probably around right here. So probably about, what would that be? Probably around, let's say, it's not quite 20, but it's like, let's say 22, in between 15, so a half. So yeah, let's say 22 megapascals. So that'd be my yield stress. My yield strain would be over here. And that's 0.1, 0.02, something like that. And there we go. That's number one. Now, let's get into some fun ones. I like these problems. So I'm going to pull up Mathematica and get this going. But I have the following metallic material under the stress state shown here. I have the force applied. So the force that's being applied here, and that's a critical force, is equal to 15 times 10 to the 6 newtons. So, first step, coordinate system. We've got it. Second step. So, there. Second step, what material we're working with? We're working with metal, so we know my Young's modulus is equal to 100 times 10 to the 9th Pascal. That's going to be our assumption. Nu is equal to 0.3. Fantastic. We're given this cube length right here, which will be important later. The blue material, initially fully fills the rigid lubricated mold. So this mold is rigid, lubricated. It's only open in the top. It's open at the top and bottom. So it's open here and it's open here. There's only, so actually it's all basically top and bottom. It's all blocked except for this plane here and this plane here. So it's open there. The thermal expansion coefficient, which means our alpha, and we know that our thermal strain is equal to alpha times delta T, is this, and the temperature decreases from room temperature to 25 C, so the change in temperatures, the final temperature is 15 minus the initial temperature in degrees C, which is 25, room temperature. Write out the full stress and strain tensor. All right, let's get at it. So we've done steps 1, 2. Now we need to do steps 3, which is write out our stress tensors and write out our strain tensors as such. So, will there be a stress? So initially it fully fills the basically this lubricated mold. So we know that there's a stress in the 2-2, and we know that that stress is going to be positive as well. We know that there's going to be a strain in the 2-2 as well. So when I pull my material like this, we should expect the material to shrink in this direction and to shrink in the 1-1. So I think that there will be a strain in the 1-1 and a strain in the 3-3, and we should expect both of these to be negative. We should expect this one to be positive. We know that this stress should be positive. Will there be any stress in the 1-1 or the 3-3? Well, there's no constraints in this problem. Basically, anything forcing there to be a restoring force. Because it's lubricated, we know everything else is 0. So we can set this up now. So what are our unknowns? So I know this. I don't know this, this, or this. So let's go ahead and solve. So let's set up our Mathematica notebook here. So we can start to define our knowns and set up our equations in Mathematica here. So we know we're working with a metallic system, so we can say that y is equal to 100 times 10 to the 9. We know our Poisson's ratio is 0.3 for metal, approximately. We also know in this problem that our alpha is equal to 3.2 times 10 to the minus 7 Kelvin. If it's Celsius, it doesn't matter anyways because it's an increment of change. So as long as you're not working in Fahrenheit, you don't have to worry about that too much. Our del T is equal to 15 minus 25. Our ET, phonom, which is our thermal strain, is going to be alpha times del T. We also know in this particular problem that our sig11 is going to be equal to 0, our sig22 or sig33 is equal to 0. And we also know that our side length of our cubes, let me just move this over here. Our side length of our cube is equal to L naught is going to be equal to 75 times 10 to the minus 3. And we know that our force in the 2-2 direction is a positive 15 meganewtons, so 15 times 10 to the 6 newtons. So that means that our sig22 is just going to be equal to F22 divided by L naught squared. So newtons per meter squared, Pascal. So with all of that set up, we can start defining our equation. So I'm going to call equation 1, EQ1 is equal to E11, which is equal to 1 divided by Y. And I need to set up this double inequality times sig11, sig11 minus nu times sig22 plus sig33, all of this plus ET. So that is going to be our first equation. And then we already have it all set up. Equation 2 is equal to this. So this is actually a very nice problem. We're just setting it up, generally speaking, as so. And then from equation 3, EQ3 equals E33, set it equal to 1 divided by Y times sig22 minus nu times sig33. Actually, why I should just be attaching that in here. And then finally, 33, and now we have sig22, sig11. And there we go. And now we can solve for the unknowns, but we should see it's pretty straightforward. EQ1, EQ2, and EQ3, and we get our values. There we go. So we've written out the full stress and strain tensor. So we've got that. Write out the principal stress values. So the principal stress values are here. And what about the maximum shear stress? The maximum shear stress would just be, if we look at our tensor here, we know what our sig11 is. And our sig22. Sig22 is our largest. That would be sig1. So our maximum shear would just be basically that 45 degrees in the Mohr circle. So sig11 minus sig22 minus sig1. Because again, in this problem, we can state that sig1 is equal to sig22, sig2 is equal to sig3, which is equal to sig11, which is equal to sig22, or 3 here. So this is our maximum principal normal stress. So if we were to rotate it for 45 degrees on a Mohr circle, it would just simply be this divided by 2. So we can look at this numerically here. And there we go. What was the rotation to principal stress? We're already in principal stress state. To maximum shear, again, on our Mohr circle, if we're looking at our sig22 here, and then this is going to be sig11, sig33 at 0. So if we're lying here, if we're rotating that 90 degrees, but we're in 2 theta space, so that'd be 45 degree rotation. Fantastic. What if I were to change this problem so that now the force pushes inward, and if the first was basically the force pushes inward. So now we're going like this, as such. So force is pushing inward as like this, and all. Let's see here. I'm trying to read out the problem. Push pushes inward, and all the other information is the same now. I'm assuming that we're still basically saying so. Basically, that the top is closed. So top and bottom are closed. So let's go ahead. Let's see if we can figure that out. So if we are going to assume, we crashed out there. So we're going to assume that, again, the only thing that we're going to change in the problem now is we're pushing inward. So it's the same problem, but now instead of stretching, we're going to push in like this. And we're going to say that everything is solid and we're only able to kind of push in like that. So what we can do is we can write out that. So we still have our material, we still have our coordinate system. So now let's write out the stress and strain tensors. So now we have a stress in the 2-2, but now it should be negative. Additionally, we know that there's going to be a strain in the 2-2, and we should also expect that to be negative. The reason why we can assume that is that, or we can assume that, is if you look at the value of the thermal expansion, it's relatively small compared to 15, that stress is huge on the system. So you can kind of assume that the compression is going to beat the thermal expansion, and actually it contributes, right? So the thermal expansion is actually contraction. So we should expect that, again, they're going to squish in here. But because of that, the pushing on this side is going to make the other sides expand out. So we should expect that there will indeed be a stress in the 1-1 and a stress in the 3-3. There will be no strain here because, again, when we push in, it's going to expand out. And it's going to expand out and it's going to beat that thermal contraction, basically the material inside. And so now we should be able to solve the rest of this problem. And we should assume that, again, if the material is pushing and it wants to expand out because we're pushing in here, we should expect the stress here and here to also be negative. So stress everywhere should be negative. All right, so let's go ahead and let's solve this problem. So we're going to go ahead. I'm going to clear everything here, but I'm going to keep my equations. Excuse me, I have a little bit of a sniffle. Everything else should remain the same. The only thing that changes is the direction of this force. And we're not going to set sig11. We're going to say E11 equals 0 and E33 is equal to 0. Again, if we had and it had to be an enormous thermal contraction, we might be thinking of a different scenario. But if you look at the thermal strain, actually, we can look at that right now. The thermal strain is extremely small. So you're looking at micro strain. And if you look at some of the other, even just simply like the uniaxial, actually, we can kind of take a look at this. This is our thermal strain here. If you look at, for example, nu times sig 2-2, which gives you some idea of basically the contraction in the other direction. Actually, nu, and then we'll divide out. You'd have to look at this, divide out by y. You see it's huge compared to this. So that gives you some rough idea. Again, this is a tougher problem because you have things that are going the opposite directions. But anyways, so we have this. Let's go ahead. We'll shift enter. Everything looks good. It's in terms of our unknown variables. So what is the strain in the 2-2, 3-3, and the stress in 1-1? So let's go ahead. Ask Mathematica to nicely solve. And negative strain, negative stress, because it needs to push back and compress as that material wants to expand out. We got it. So, right at the full stress strain. Well, now, what are the principal stress values? Again, we do have principal stress here. So we have sig 2-2. And then, let's look at this. So again, our sig 1 is going to be the most positive. So sig 1 is equal in both senses to this value right here. And our sig 2, or basically our sig 3, is going to be equal to this. So we can see this right here. is negative. So if we're looking at, again, our maximum, the rotation to principal stress is still going to be 0 because, again, we only have normal stresses. If we're looking at the value of maximum shear, it's just going to be sig 1 minus sig 3 divided by 2. So this would be that value for maximum shear stress, and it'd be a 45-degree rotation again. Fantastic. All right. Turns out the wall was not entirely frictionless. So there was another stress measured to be this in the stress in the 1, 2. So write up the full stress and strain tensor, write up the values of principal stress, et cetera, et cetera, et cetera. Now, there should be a caveat here. Again, there should be a very big caveat. We're looking at this should only be for the first problem scenario. So the first scenario. So we're not building upon from the last one. So in the first scenario, we said because we were pulling, we had a stress like so. We had 0, 0, stress in the 2, 2, which we had calculated before. Now we have a stress in the 1, 2. So now we have stress in the 1, 2. And we also have now a strain tensor that's going to look like there's going to be a strain in the 1, 1, a strain in the 3, 3, a strain in the 2, 2. There's also going to be a strain in the 1, 2, and a strain in the 1, 2 here. So we need to solve these problems. So let's go ahead. We're going to quit the kernel, quit it locally. We're going to go back to the first problem, and I'm going to make sure we have some caveats here. Now we're saying this is positive, that sig 1, 1 equals 0. Sig 2, 2 is equal, sig 3, 3 is equal to 0. And we also have another equation where sig 1, 2 is equal to minus 36 times 10 to the 6. So we have all of that good stuff. Boom. We're going to have one more equation here where we have EQ4 is equal to, so the strain in the 1, 2 is set to equal to 1 over y times, basically 1 plus nu times sig 1, 2. So we could have that. So now we have equations 1, 2, 3, and 4. Let's find my mouse. We're going to shift enter all of those. And we're going to solve for the 4 equations, even though they're already solved there. So EQ4. So there we go. So we have those values, and they'll look very similar to the previous problem. Now, stress and strain tensors we've got, but what we don't have is these now, because we have shear stress and because we have plane stress in the 1, 2 plane, we are not in principal stress. So we are going to have to go, and we're going to have to open up, because unfortunately my things just crashed. Actually, let's restore. But it didn't restore fully. Let's go ahead. Let's go. Not zoom. Let's go to our canvas. Let's go ahead. Let's look at our course. So we can actually look at several things. I would say it's probably solid mechanics this week. Probably was the last week. Let's go back to pages. Excuse me. Week 9. Oops. More transformation notebook. So again, if we're going to do our rotations, I want to pull out, I don't want plug and chug. I want to do linear algebra. So we're going to go here. We're going to set these values, and then we're going to pull out. Actually, we can jump up here. So I need to set up my plane stress state. So my stress in the 1, 2 plane is going to be equal to, I need sig 1, 1, sig normal, and then shear stress. So this would be my values. These would be my values, excuse me. So now if I want to find the rotation, so T dot my old stress 1, 2 will give you my new stress state. So if you look at this in, for example, matrix form, we kind of see these 3 equations. So if I'm in my principal stress state, the third equation, which represents my new stress in the 1, 2 direction, I need to solve when does this equal 0. So basically, what rotation in terms of theta will give me that will give me no shear stresses, basically when I'll be in the plane stress state. So I can pull out, again, 4 values. Why? Because we're doing circular symmetry. So this would be the angle, 0.773. If I'm trying to find the value of the maximum, and if I want my values, all I have to do is do t.stress 1, 2 slash dot theta goes to this value. We can confirm it. So if I do this rotation, this is my new stress in the 1, 1, my new stress in the 2, 2, and you see here this is basically and effectively 0. If I want to find my maximum shear stress, we're going to take the derivative of this equation with regards to theta and set that equal to 0 because we want to see where's my shear stress maximized. And I can pull out the value. We can just say, and notice here, look at it's 45 degrees because we're going basically, if you do that rotation counterclockwise positive, we're going to have to rotate basically another direction. But anyways, actually we can pull out. This is going to be a huge value, but we can see a couple of circular symmetry values. Basically moving in the opposite direction, or better yet, this one's a good one. So you can see kind of, this should be hopefully negative 0.773. You can kind of see that the rotation here. So this would be like the 45. If you did 45, for example, minus 0.773, you get something similar to this. But anyways, and if we want to see the value, you do t.stress 112 or 12 slash dot theta goes to what? Theta goes to, and then we can just pick out one of these values. Doesn't matter. Signs may change. The magnitudes are important. Same value here because we're at the center of our Mohr circle, and then you see the value here. So we got it. Fantastic. So let's go back to our problem. Maybe it's so we got it. So all the rest of these problems are solved. Fantastic. All right, so let's go to the next one. I am going to delete these things. And let's go ahead and look at the pipe. So now I'm working with a polymeric pipe with length, thickness, diameter already. Okay, so first thing I'm going to do, I'm going to draw my coordinate system. My coordinate system is going to be something that looks like this. I'm going to do this in the 2 direction, this in the 1 direction. Again, I'm wrapping around. My coordinate system is cylindrical, so it's going to be 2 is going to wrap around this direction, 1 is going to be along that direction. So I am a polymer, so y equals 1 GPa. My nu is equal to 0.4. And if I have thickness and diameter, I need to immediately start to think about what? You guessed it. Thin-walled pressure vessel, specifically thin-walled pressure vessel. So I'm going to quit my kernel here. Excuse me, sniffles. So I needed to find the length I don't care about. That's an information that I don't necessarily need. So my radius is equal to 15 meters. My thickness is equal to 0.5 meters. So I need to see, is r divided by t, is it greater than 10? If so, I can deal with a thin wall. Yes, it is. Nu is equal to 0.4. I know that my sig h is equal to del p times r over t. My sig l is equal to sig h divided by 2. My eh is equal to 1 divided by y. Sig h minus nu times sig l. My el is equal to 1 divided by y times sig l minus nu times sig h. So we've got those values. We're told that the strain gauges measures through 2 strain gauges, strain measures in the strain measured in the 1 direction. So basically, for the strain gauge 1, it is measuring. So basically I can solve that my EL, because it's my longitudinal direction, equals 0.01. So I can solve, that's my del P. So del P is equal to this. But I see I've forgotten something here. I'm given this information. I'm given it's a polymer. I've forgotten that I need to take into account ET plus ET. Uh-oh. Okay. So, and I know that ET, how am I going to solve this problem? So I'm given the strain. I don't know what del P is. I know that my del T is equal to, from room temperature to 55, so 55 minus 25, that's my del T. So how am I going to solve this problem? And I know that my ET is equal to alpha times del T. So if I look at this, it gives me my solution in terms of alpha. So this is a little bit tricky. Now, I could EH divided by EL. Let's do full simplify. Let's see, how can we solve this one? Well, one good way we can solve this problem is if we look at our notes, and I know that I always say don't do this, but again, one of the ways, because we have an unknown in this problem, we are dealing with polymer. So we have said, and we talked about when we're looking at thermal expansion. Where's my thermal expansion? When we look at thermal expansion for polymers, 50 to 500. So let's just say my alpha is 50. Let's say over here, let's say my alpha equals 50 times 10 to the minus 6. Get this right here. This is my ET. This is my EH. This is my EL. You can simplify those now. Oh, why isn't that simplified? EH, EL. Full simplify. EH divided by EL. Yeah, anyways. We can solve this. So this is our del P. We're going to expand out. Oops. Del P is equal to this. And now we can write out all of our values. EH, EL, sig H, sig L. We got it. Fantastic. Let's go back. Write out the full stress and strain tensors. We got this. Pressure. Are we in the principal stress state? Yes. What is the value of maximum shear? Value of maximum shear is always going to be sig H minus 0 over 2, which is equal to sig L, which we already found here. Find the stress state at a 17 degrees clockwise rotation from the maximum shear stress state. Ooh, I like this problem. So let's go ahead. We'll evaluate up here. So let's go ahead. So I need to find now my stress. I'm going to go over here. So let's see what the problem's asking us to do. So I need to do, basically cylinder stress. I'm just going to call it C stress. C stress is equal to sig H. Actually, let's do it properly. It's going to be sig L because that's in the one direction. Sig 1, sig 2 is sig H. And I may have, again, in this problem with this notation, our stress tensor was sig L, sig H, 0, 0, 0, 0, 0, 0, 0. There we go. So let's go over here. Sig H, sig L, and then we have no stress here. So if we're looking at, actually, we already know this problem. The stress rate, because if we're looking at here, we're looking at sig H, we're looking at sig L, somewhere around here. So the rotation, so first we have to go, and we can go first counterclockwise. So we have to go, this is our maximum shear, so we have to, from our initial stress state, we have to go 45 degrees counterclockwise, counterclockwise. What am I talking about? No, I'm trying to think my directions. I go from here to here. No, I'm going clockwise. Excuse me. Clockwise. So we need stress state from 17 degrees clockwise from the rotation from maximum shear. So I would actually do another. So we have to go from here all the way to there. But again, this is more circle stress state. So this is what I'm talking about where this is confusing to me all the time. But we can do it. So I need 17 degrees clockwise more. So in more circle space, that would be another value here. So 45 plus 17. So I need to do basically a clockwise rotation of 45 plus 17, but that's going to be negative because we're going clockwise. So I need to do T.stress dot C stress, and I do / dot theta goes to, and I'm again 45, so we need to do clockwise. That's basically minus 45, and then 17 degrees again clockwise. So this will be the value. And you can confirm that with Mohr circle. But isn't that so much nicer to do with our linear algebra approach? All right, ceramic mold. Again, so coordinate system, 1, 2, 3. Ceramic material, so Young's modulus is equal to 300 gigapascals. Nu is equal to 0.2. So it's a rigid box with the only thing that's open is the top. We have the length right here. Temperature increases from room temperature. So room temperature to 100 degrees C. So let's go ahead and do it. So when this material expands, let's go ahead and write out our third step, stress and strain tensors. So all we do is increase temperature. So now when I look at the 2-2 direction, it wants to expand out. So there is going to be stress. There's not going to be strain here, but there will be stress in the 2-2 and it should be negative. There's not going to be, so we're going to have a strain in the 3-3 that's positive because the top is open. There's not going to be any strain in the 1-1 either. So we're going to have a stress in the 1-1 that's going to constrain that, which should also be negative. There should be a stress in the 2-2, which should also be negative, but there will be no stress in the 3-3. So let's go ahead and let's work through this problem. So I'm going to go ahead and once again, I'm going to quit the kernel. I am going to go back. I know this isn't best practices, but I'm going to go back to the top. We're dealing with a ceramic material, so we're going to change this to 300. We're going to change this to 0.2. We're not given, once again, this is tough. We are not given a thermal expansion coefficient. We are given the room increase from, so basically 100 minus 25. So for a ceramic material, we can go ahead and say it's about, let's say 1 times 10 minus 6. So let's go ahead and just give it that so we can solve this problem. Our L naught is going to be 50 times 10 to the minus 3. We don't know what the force is here, so we don't know what the sig 2-2 is. We know that the sig 3-3 is 0, and we also know that the E11 is 0 and the E22 is 0. So with that, we can look at those values here. Let's look at those just to take a peek. So we have equation 1, equation 2, equation 3, because we have 3 unknowns. What are our 3 unknowns? E33, sig 11, sig 22. And we can go ahead and solve. Like that. And there we go. Kind of makes sense, right? E33, it should increase, and then sig 22 and sig 11 should be equal, and then we're constraining that motion. And then it says determine the final length. So the only strain, because all the other strains are 0, the only strain is going to be this. So strain is equal to, so let's go ahead and solve. The strain will be equal to my L final minus L naught divided by L naught. So there you go. That's your final length in that direction. Now the temperature decreases from room temperature to 0. So now, again, I'm going to just delete that. So we're going to go ahead, actually, let me erase. So if we decrease temperature now, what's going to happen? So if I decrease temperature, my stress is going to be equal to here. My stresses are all 0, 0, 0, and there will be strain in the 1-1, strain in the 2-2, strain in the 3-3. That's it, because again, it's decreasing, it's contracting, and there's nothing that's saying, again, that we're kind of constrained effectively. So let's go ahead and let's solve it. So we can go ahead and start to plug this in to our Mathematica notebook. So we have our material. Let's go ahead and just double check this. The final lengths in all directions, which we did that previously. So now we can go ahead, set this. We have our alpha that we, again, pulled from our lecture notes. So now every side is going to be contracting because we're decreasing in temperature. So sig 11, sig 33, sig 22 will all be 0. And we can just go ahead and calculate these out. And when we do that, we should have our solution here. Actually, everything is calculable, so we'll be good to go. And then we can find out the final lengths as well. And we should expect that basically all of these values will be equal to one another. And I'm going to actually make sure that we log in here. But it's just thinking. Got to make sure we'll run the notebook. Make sure that the evaluations were connected here. Let's go ahead. We're going to quit here. Yes, didn't like that I wasn't connected with a license, but now we should be good to go. Let's run it. Now it's thinking. It's connected. We're making sure that we're connected. And there we go. So we find, and we have all these values. So for every side, the final length will be this. So there we go. So we've got it. So we can go ahead and actually let's make sure our alpha. Sorry, 1 second here. I want to make sure that we did go from. Ooh, excuse me. That's wrong. Excuse me. So you have to be careful. Decreases from room temperature to 0, so 0 minus 25. So this will be our actual solution. I knew it was odd that it was expanding because we should be contracting. So we should see this, and then we get this. And now we go. We see it shrinking. So there we go. So let's go ahead and do, we've gotten that one done. Let's go ahead and erase here, at least everything inside. All right. So let's go ahead and draw. Repeat both these questions. Both of these questions. But now the material is physically attached to the cube everywhere. So it's attached at the bottom, but it is still open at the top. So let's go ahead and do our increase. So if it's attached everywhere, it actually doesn't really matter necessarily. But for each of these problems now, if it's attached, we're going to have stress in the 1, 1. We're going to have stress in the 2, 2. And we will not have stress in the 3, 3 because whether it expands or it contracts, it still can, it's open in this top section. So again, the top is open. And we're going to have no strain here, but we will have strain in the 3, 3. So each of those problems will be exactly the same. So let's go ahead and actually just do the previous one, except now we know that there will be a stress in the 1, 1. The sig 3, 3 is 0, and now we know that our E1, 1 is 0, and our E2, 2 is 0. So let's do the problem we just did first, which is going from room temperature to 0. And we can go ahead and solve that. So let's go ahead and reevaluate. Ooh, again, that's why you quit your kernel. So let's quit our kernel. Let's evaluate from room temperature to 0 degrees C. So we can go ahead and solve this. Room temperature to 0 C. Again, once you restart that kernel, it's going to take some time. And then we'll do the same thing for going from room temp to here. And you can see the stress values there. And again, we can just plug this in here and find that final length as such. And lastly, we can go ahead and now go all the things. The only thing we have to change here now is actually going from 100 to 25. So again, quit the kernel, quit everything. There we go. And then now we can run this one more time. And shift enter, and we'll be good to go. Very good problem. I like this problem. So let's finalize this one, and then we can go and get ready here. And there we go. And let's do one more time. Makes sense because the temperature is increasing. The stresses now are negative. So everything, that's the nice part about solid mechanics, is that it all kind of makes sense mathematically in the end. Fantastic. So we just have one problem left. So let's go ahead and let's get started on number 5 now. All right, so we have a metallic material that is the orange curve on the stress strain curve that's in a rigid box is only open in the direction where the force is being applied. I need to design this material such that the strain in the 2, 2 direction does not exceed the strain to failure of the orange stress strain curve. So I need to design it so that it doesn't exceed this. So we can't have the strain to be equal to basically 0. Let's call it 68. Okay, so we have a coordinate system. Let's define it. 1, 2, 3. We have a material. We said it's a metallic material. Metallic material. So y is equal to 100 GPa, where nu is equal to 0.3. It's closed everywhere except where we're applying the force. So it's filling the cube as usual. All right. So we've got those things, or not those things, those steps. Step 1, step 2. Now let's do step 3. So there will be a stress. So we know that there's going to be a stress in the 2-2 for sure. We're applying that. It's going to be compressive. We know that when we push in on this box, it's going to want to expand the 1-1 and the 3-3, and there will be a stress in the 1-1 and the 3-3 because we're going to have a strain value here. It must be 0 here and 0 here because it's constrained. And so now we need to figure out what's the strain of the 2. And we know, so we can solve now for the strain in the 2-2, which we know has to be basically, to make sure it doesn't exceed. What is the question asking us to do? Does not exceed. So we just need to make sure it's, basically 0.68. Yeah, so this needs to be, and actually because we know that we're pushing in, the strain is going to be negative 0.68. So that's a very important caveat there. So let's go ahead and let's solve the problem. So we're going to pull up our notebook. We are going to, again, quit the kernel. Let's go ahead and quit. In this problem, do we have any temperature changing? No. So this is a nice problem because we don't have any temperature changes. So we can go ahead and get this moving. So let's make sure our Mathematica is going like so. So we can forget about alpha and delta here. So I'm just going to change delta, to 0. We're going to change our Young's modulus because it's a polymer. We're going to change our nu. We're also, excuse me, we know that there's going to be only, that our stress in 2-2 will be minus 0.68. I believe that we said that there's going to be no strain in the 1-1. So E11 is 0, E33 is equal to 0. Our L naught is 50, so we should be good to go. All right. Let's go ahead. And again, we can keep this ET because ET is just going to be 0 because we set the del T to 0. So get Mathematica running, get everything thinking, wrap up this problem. Here we go. All right, so let's go ahead and set up our 3 equations. Here. Everything is just sig 1, sig 2, sig 3. We can go ahead and set up and solve. And these are all negative, which makes sense because, again, it wants to expand, but it's basically constrained in that direction. So fantastic. So right at the full stress and strain tensors, what are the final dimensions for this material? So all we have to do here is, again, just need to take out the strain. We already know the strain is going to be this. So we know our L naught as well. So that's going to be our final dimension. Excellent. Let's go over here and make sure we weren't in percent here, right? Yes, we weren't in percent. Fantastic. Final dimensions, we got that. What is the force exerted in the 2-2 direction? So we know that the stress in the 2-2 is this. So if I want force, I'm just going to go ahead and solve that my stress equals this is just equal to force in 2-2 divided by L naught squared, because it's a cube. Be careful if there's like a rectangular dimension, but there we go. We got it. So that would be your force. Fantastic. What is, we did this problem again. Let's see, we got this here now. What is the stress rate at a 47 degrees counterclockwise rotation from the principal stress state? So we are here in the principal stress state. Now, are we in plane stress? No. So The rest of this problem we cannot solve because we don't have those tools. You're going to have to come and visit me in a more advanced course for that answer. So that's it. So those are the problems. Congratulations, Pset 5, which is one of the most difficult but most important for your exam, is done. So see you in the next video. Thanks. Bye.